Okay, I think we're going to go ahead and start back up here. Chen, are there any, or Paul, any questions from the chat that have come in, or any new questions? Okay, so for the remainder of the workshop, we're just going to focus on different examples, and then we'll still have some time at the end for questions if they remain once we're done here. So. Okay, now if you want to at this point, you can follow along live, right? So if you have SAS or Stata installed on your laptop and you want to follow along with these examples live, this slide shows you how you can download the SAS and Stata data sets and just follow along with the code that I'm using. This is entirely up to you. So I'm just showing the code for these different examples, but if you want, you can at least follow a couple of the different examples live as you go. So if you go to the website for our book, Applied Survey Data Analysis, and that's listed at the top of the slide, you'll see there's a link under data sets for analysis examples data sets. Just download that zip archive, and if you save that somewhere on your machine, in that data set you'll find two different versions of the NHANES data, one with a SAS format, one with a Stata format. They were also made available via email, I think. Yeah. So they were also emailed to you as part of the workshop. So again, you can just follow as I'm talking, or if you want to try to type along as we're going, that's fine too. You can return to these slides later. They're available on the PDHP website if you want to follow along later, but you have that option at this point if you want to read the data sets in the either piece of software. Okay. So just a couple important notes about software. The survey procedures in SAS, these procedures are readily available. You don't need any kind of special package or anything like that. They're part of SAS Stat. So you get all the other data management capabilities that are built into SAS. There are some minor limitations in terms of different types of regression models. So there's not really a general purpose generalized linear modeling tool yet that's been adapted for design-based analysis. So for example, if you want to fit a Poisson regression model or a negative binomial regression model or a gamma regression model, there's not a survey procedure for that yet. Been that way for a while, not exactly sure why, but hopefully in the near future releases, that capability will be there. We had a student in an ISR Summer Institute workshop a couple of years back who was so perturbed by this development that he went off and wrote his own macro to do this stuff, and he actually wrote a paper about it, so you can go out and download his macro if you want to do that. But I just don't know why staff hasn't added it yet. But every new version adds more flexibility and features. So hopefully, again, with new releases, that would be possible. I mentioned in Stata earlier, I think the SPY commands are the most far along in terms of adapting to different kinds of analyses. Very easy to set up different kinds of variance estimation. A lot of Stata's graphing commands, too, enable you to specify p-weights. So that's a nice feature, so you can get a weighted visualization as opposed to an unweighted visualization for like box plots or histograms or scatter plots or whatever it might be. R is also very good at that as well, incorporating weights into visualization. So that's nice. But again, there's many more modeling options in Stata as compared to SAS, at least at this point in time. Okay, so I'm just going to go through a variety of different examples of estimating different kinds of parameters. This example is just starting with totals. So this is where, again, your objective, what you're trying to describe for the finite population is a total. Like how many people have a disease, how many people voted, whatever the case may be. One of the key messages in this example is to be aware of what are called normalized survey weights. Okay, so sometimes when you download a survey data set, you'll find a weight variable that has a mean of 1. And that weight variable sums to the sample size. It doesn't sum to a population size. Okay? So for almost every other kind of analysis, aside from estimating totals, those normalized weights are fine. Okay, there's no problem with that. Again, they sum to the sample size. Their average weight is 1. That's fine. Where you run into problems with normalized weights is when your analysis objective is to estimate totals. Okay? Because with those normalized weights, they only sum to the sample size. So if, for example, you're trying to find out in the U.S. population how many people have ever had a major depressive episode, your weighted estimate might be something like 469. So I often joke with students about this in our classes. I say, are you literally going to write a paper that says, based on your best analysis, you estimate that there are 469 people in the United States who have ever had major depression. You're going to do that? That's kind of the critical thinking aspect of this. Okay? The reason that's happening is because the weights were normalized. So in these situations, if you want to estimate totals, you have to rescale those normalized weights back to the population scale. And the way you do that is, this is in that first gen statement here for STATA. You need an estimate of the population size. That's that 209 million number, in this case for the National Comorbidity Survey. And then you need your sample size, which in this case was 9,282. That removes that normalization from the weights and puts them back on a population scale. Okay? Don't need to do that for any other estimates, just totals. Okay? So it's unnecessary to do that for anything else, just totals. So because my objective in this example was to estimate totals, I did need to rescale those weights. So I'm creating a new variable called pop weights that does that rescaling using the original NCSR weight. Okay? Then I have my survey set command. In the NCSR data set, this is SE cluster. That's the name of my cluster variable, back to an earlier question. Okay? So again, I just need to read the documentation and find out what the appropriate cluster variable to use for variance estimation is. My weight variable is that pop weight variable I just created. And then my stratum variable is SE strat. Again, coming from the documentation. I didn't make that up. The last thing you want to do in these kinds of analyses is make up your own stratum and cluster variables. Never do that. Okay? You never want to just say, I think gender should be my stratum variable, or I think hospital should be my cluster variable, when that's not what was actually used for the sample design. You want your standard errors to reflect what actually happened in the sample design. Okay? So never make up your own design variables. Always use what the documentation is saying should be used for variance estimation. So that's what we're doing here. Okay, okay, then the command itself, I say SVY total. That's the analysis command. My binary indicator that I'm summing is MDE. So that's an indicator of whether or not you've ever had a major depressive episode. Okay? And I'm not doing that for the overall sample. I'm doing that for different subpopulations. So another way to do subpop analysis in STATA is with this over option. What over does is it repeats that analysis using the appropriate subpop approach for each category of that over variable. So I'm getting an estimate of this total for each level of 3-category marital status. Okay? Those are the point estimates that you see in the table here. And I'm doing that correctly by using the over option. I'm not using if or where or by or keep or anything else like that. Over is specifically designed to do repeated subpop analyses within STATA. Okay? The mat list post-estimation command, by default with very big numbers, STATA uses scientific notation. I bet some of you have run into that before. Okay? That command, mat list, just gives you the actual estimates that were computed in the analysis. So if you need to report those and you don't like scientific notation, that just lists the actual point estimates. And then finally, ESTAT effects, that lets you calculate what are called design effects. And that's the inflation in the variance of an estimate due to the complex sampling features. And I show those design effects in the last column there, that column labeled D squared of Y hat. That's the multiplicative effects on the variance of these estimates due to complex sampling. So what that's telling me is that for the married subpopulation, that estimate of 20 million people who have ever had major depressive episode, the variance of that estimate is being inflated by 6 times due to the aggregate effects of cluster sampling, weighting, and stratification. So weighting and cluster sampling won that tug of war in this case. There's a 6-fold variance inflation due to complex sampling. And we're accounting for that in that linearized standard error that you see there. Okay? And you see the design effects go down for smaller subpopulations, like separated, widowed, divorced, and never married with these total estimates. Yep.
I'm just trying to think about the intuition behind why the design effect is so high for the married group.
Yeah.
Is that because it's like the majority of the sample is in that group, and if
Yeah.
you looked at the overall sample, you would probably get that.
Right. So long story short, another way you can think about design effects, this multiplicative change in the variance, it's a function of the average respondent count within each cluster and that within cluster correlation. There's a formula you can write down. So in this case, the design effect is really being dominated by that average respondent count per cluster. So Jeff, you were right with your intuition. The bigger design effect is coming from the fact that you simply have more people in each of the clusters that are prone to this within cluster correlation. Okay. Okay, so you see the weighted estimates of these totals, the linearized standard errors, the 95% confidence intervals using the correct t-values and the correct degrees of freedom, and the design effects. You don't have to report the design effects. The key is that you're just accounting for these in the analysis. I'm just displaying them here for illustration. Okay? So that's totals. Questions about this approach for totals? Any questions here? Again, we don't need that rescaling of the weights for any other estimates, just for totals. Okay. Here's the corresponding SAS code. So you can see I just created a data set that has that rescaled weight variable in it. And then in the subsequent procedure, I use the pop weight in the weight statement, along with the stratum and cluster codes. Notice also for my subpop analysis, I use domain. So that's the SAS version of subpop. So if I want to do subpop analyses, I need to add that domain option. Not use where, not use by, not use if, okay? Use domain. It's pretty funny actually. Stata takes kind of the heavy-handed approach and doesn't print a standard error for you. If you do subpop analyses correctly and you throw out clusters, you just simply don't get a standard error. SAS will go ahead and run the analysis. It'll give you output. It'll give you estimates that look reasonable. And then as a note in the log, it slaps you on the wrist. There's literally a blue note in the log if you use where or by or whatever it is. There's a blue note in the log that says, you didn't do this subpopulation analysis correctly. So if you're not in the habit of checking your log every time you run a procedure like I am, like I had a manager long time ago when I interned at Deloitte & Touche, I had a manager when we were running SAS code, he's like, do not show me a log unless it's black and blue. He's like, if there's a single green or red thing in your SAS log, I will not look at your results. So I kind of got molded into that approach by that particular guy. But if you're in that habit, you'll see like a paragraph, blue note, that says you're doing the subpopulation analysis incorrectly. It's not valid for if, by, or where commands. Here's how you should be doing it. Like you may want to revisit your analysis. But it's a note. It's not a warning. It's not an error message. So if you're not in the habit of checking your log, you might just report that output. So SAS users, be aware. Just use the domain statement if you want to do these kinds of subpop analyses. Okay. Now, a little bit of a misnomer. To get totals in SAS, you actually have to use proc survey means. There's no proc survey total. Okay. You have to use proc survey means and then add that sum option. That's where you get weighted estimates of totals if you're a SAS user. Okay, means and proportions. Not much changes here. In SAS, you'd want to use proc survey means. In Stata, you would just use SVY mean. So in this particular example, I'm using the HRS, and I'm calculating mean total household assets. So my stratum variable in HRS is stratum. My cluster variable in HRS is SICU. Again, this is the naming thing. You really have to take a look at the documentation. SICU stands for Sampling Error Computation Unit. So those are the sampling clusters that HRS has provided to you for the purpose of estimating sampling variance. You talked to David Weir, you told him you didn't use the SICU variable, he's going to get pretty upset. A lot of work goes into that. Okay? So you get these variance estimates, and there's year-specific weights. This gets back to the longitudinal stuff. So in this particular year, the weight was K weight for the households. Other years will have different initial letters. Okay? Again, I use the domain statement. I want the report from the financial reporters of the households on this particular variable. So I want that particular subpopulation. And then my variable is just a measure of total household assets that was collected in the survey. So in Stata, I declare my design variables. Again, cluster variable first, P weight in parentheses. Another thing about Stata, don't use A weights or I weights or F weights. Stata makes all these random kinds of weights available. There's only one weight that matters for what we're talking about today. It's a P weight. Don't use any other weights for design-based analysis. You will not get the right answers. And some procedures flat out won't work. So only use P weights within Stata. Okay. Then my stratum variable. Here's an example of using that subpop command. You can either input a dummy variable in parentheses or use a condition. Some people like writing these subpops using conditions. So I can say if K fin R is equal to 1, that's equivalent to just plugging in an indicator for that subpopulation. I can go either way. Okay? And then my base command is SVY mean, and then I can ask for design effects if I want. So here's the unweighted sample size. Note the degrees of freedom. Okay? Sample size is 11,942. Degrees of freedom for the critical T value, 56. Again, because it's a function of how many HRS clusters there are. It's not a function of sample size. The clusters are what's used to estimate the variance. Okay? I have my weighted mean. I have my linearized standard error. I have my 95% confidence interval, and then the design effect. So for this fully design-based analysis, my inference would be based on that 95% confidence interval that reflects all the sample design features and uses the weighted point estimate. Okay, questions about this example? Everybody with me? Any chat questions? Okay, so hopefully you're getting the message that it's pretty easy to do this stuff. A little bit of a head scratcher why people aren't doing it. Okay, percentiles. Another kind of descriptive estimate is percentiles. Okay? If I want estimates of percentiles in SAS, I can use proc survey means. Another kind of misnomer. In the proc survey means line, I can add all different kinds of quantile indicators. So if I want a 34th percentile or something like that, I can use Q34. Okay? So I can change those options. In this example, I asked for the first quartile, the median, and the third quartile. Okay? So this is the 25th percentile and the 75th percentile. Okay? Stratum variable, cluster variable, weight, domain statement, variable, all I'm changing is the estimates that I want within survey means. Okay? And I get my weighted estimates, my standard errors. Stata, so Stata just released version 16. Has anybody used 16 yet? I sort of still slowly installing it, so I haven't had a chance to play with 16 yet, but as of 15, Stata did not have a SVY percentile command. It's one of the only limitations where I pointed Stata as having a shortcut. And the reason for that is because variance estimation is not as straightforward for percentiles. There's not kind of any clear-cut winner approach, if you will. So it may have been fixed in 16. I don't know. I just haven't had a chance to look at it yet. But this is an example of a built-in procedure within SAS for survey mean, or for quintiles. There isn't any analogous procedure in Stata as of right now. There's a user-written command called EPC tile. My friend Stas Kolonikov has written that. It's a user-written command. You can use it. He's proud of it. He thinks it works correctly, but it's still user-written. Okay, so some people don't want to see user-written commands, but that's an option. So EPC tile is an option for design-based percentile analysis within Stata. And I can help you install that and work with it and so forth. Jeff?
Can I just go back to means and proportions?
Yeah.
Another question.
Yep.
So let's say that you're lazy and you have one line of code that does both means and proportions using like the mean command.
Yeah.
And you include some binary variables. Where are you going to go wrong with those binary variables?
Oh, great question. So if you're a Stata user, you think back to the NIS example, how I was listing prop over and over and over again. If you're a Stata user and you plug in multiple variables to SVY mean or SVY prop, it uses listwise deletion.
Oh.
So
it won't estimate it for you.
Right. Well, no, it'll estimate it. But if one of those variables has like 11,000 responses and another variable has 9,000 responses, it'll only analyze those 9,000 cases. So you're throwing out data.
Okay, but what about like the continuous versus binary variable?
Doesn't matter.
Okay.
Yep, doesn't matter. So my recommendation in that case would be if you're doing your descriptive analysis, use separate mean and prop commands for each variable. It's a lot of lines, but it's necessary because otherwise you're throwing out data. Okay, so that's percentiles. Categorical data analysis. So I'm just showing examples here for multinomial variables. Same thing applies to binary variables if you're just doing proportions. In Stata, you would use SVY tab to create weighted frequency tables. In SAS, you would use proc survey freak instead of survey means. So here's an example of analyzing N-Haynes data within SAS. So we'd say proc survey freak and then the name of the data set. Declare your 3 design variables for this data set. This is from the N-Haynes data. So the weight here is an examination weight. So I'm analyzing data that were collected during a physical examination. And again, you see different stratum and cluster variables. There's no common standard for how these variables are named. So for in N-Haynes, they're called SDMB stray and SDMB PSU. Okay? Completely different from everything else we've looked at. Remember HRS, they were called SIKU for the cluster. So there's no common standard. It requires you to read the documentation. And if you're reading documentation, especially because we're working on this paper right now, if you come across some really crummy documentation and you can't figure out what design variables to use, send them to me. We'll put that in this paper as a one-star example of documentation. We're really on this kind of grassroots campaign to make life easier for data users. So I'm more than happy to help you try to parse documentation that's otherwise hard to read. Okay, another point about this code, for whatever reason, of all the survey procedures in SAS, Survey Freak does not include a domain statement. Another kind of head-scratching thing, but it is what it is. So if you want to do sub-pop analysis within Proc Survey Freak, the domain variable has to come first in the table state. Okay? So if you want to restrict your analyses to particular domains within SAS, age 18P in this case is my domain variable. I have to list it first in the table statement before the rest of my table variables. Okay, so that's just an idiosyncrasy for SAS users to be aware of. If you want to use the domain, a domain analysis, make sure to put that variable first in the table statement. Every other survey procedure has an explicit domain statement. This is just kind of a weird thing. Okay, and I just list my categorical variable. In this case, it's BPCat. Here's the Stata code to do that same analysis. So I declare my survey features, cluster, weight, stratum. I run survey subpop using the right subpop approach, and I say tab BPCat. That's my categorical variable. Okay, pretty straightforward. That's the frequency table I want. I can ask for design effects. Another way to get the same results is using prop. So prop is another analysis command for computing proportions. You'll get similar results. And I'll come back to that distinction here in a second. So for all four of my categories of this variable, I get my weighted estimate of the population proportion. So again, thinking about language, in my paper, I would say that I estimate 47.1 of the NHANES target population to have normal blood pressure. I would not say that 47.1% of NHANES respondents have normal blood pressure. Everybody see that distinction? We have the power when using these weights to make population statements. That's what's critical here. Okay? I get my linearized standard error, my design-based confidence interval, and again, I've printed design effects just to give you a sense of what typical variance inflation might look like due to the complex sample design features. So, Jeff?
So one kind of counterintuitive thing about the Stata command here is that if you took the survey prefix off of that tab,
yep,
then you would not get the proportion to the total for
right.
counts, right?
Counts, yep.
So I'm assuming when you run that in Stata, you're only getting the proportions, you're not also getting.
Yeah, I added, so good question. I added the OBS option so I could get the counts.
Okay.
Yeah. So that OBS option there will also print the unweighted counts, the unweighted sample sizes in the frequency.
Cool. All right.
Other questions about the syntax here?
How about syntax? Could you just say that statement again about the you just said it, like the population.
Oh, yeah, I responded.
Yeah.
So what you do want to say is we estimate, you don't want to say it with certainty because it's an estimate. We estimate that 47.1% of the NHANES population has normal blood pressure. You do not want to say 47.1% of NHANES respondents have normal blood pressure. We want to make an inferential statement about the population, not about what the respondents in this sample did. Other questions about the categorical frequency table here? Other questions? Okay, I do want to say, so I mentioned that other article about multiple imputation earlier. This is another literally hot off the presses article that I was fortunate enough to review actually, about forming confidence intervals for proportions based on complex samples. And the issue being addressed here is the coverage of confidence intervals for proportions. So basically the message is that the standard plus or minus t times the standard error approach of forming a confidence interval is horrible for proportions. That's the message in this article. Don't do it. The tab procedure in Stata actually computes what's called a logit transformation. That's a little bit better than horrible to form these intervals, but still not great. That's what these authors are saying. So this brand new article outlines really kind of state-of-the-art methods for forming confidence intervals for proportions that have the stated coverage. That's the key thing. So if you say you're forming a 95% confidence interval, you want 95% of those intervals to cover the true population parameter. Those walled intervals, the coverage becomes like 60, 70. It's just not good. Okay? Now, my beef with this article, because I was a reviewer, I wanted them to provide our code. I said, it's really cool what you guys are doing. See how to implement it. Readers are going to want to do it. Okay? It's straightforward. Pretty much anybody in this room could follow what they're doing, write a little code to do it, but just provide some R code. And the editor agreed not to have them provide it. I don't know why. But if you look at the supplementary materials, it just gives you the data. Okay? So one thing that I think I'm going to have Chen work on is writing the R. You didn't even laugh. Is writing up the R code from this article that we can just distribute to people. Okay, to just make sure that you're computing confidence intervals that have the appropriate coverage. But this again, just brand new, just came out, and there's been a lot of work that goes into this area. In Stata, just make it clear that you use that kind of logit transformations, I say here, to form the intervals, and see if your inferences would change depending on which approach you use. I think that's the best way to go about it. Okay?
So you're talking about the coverage property.
Yep.
What other possible properties are there that would justify using these other?
No, that's it. That's what the entire article is about. Just whether these intervals have the stated coverage or not. Yep. And Rod's a big stickler about that. Rod was one of the co-authors, and yeah, they tear down like what most software is doing by default. Interesting. For proportions. The issue here is where you get that uncomfortable situation where your weighted estimate of a proportion is like 0.01, and your lower limit in the confidence interval is like negative 0.05. I mean, that's the intuitive idea here, is that that interval makes absolutely no sense because a proportion can't be negative. That's the basic issue here. So, okay, so if anybody would like to see a copy of that article, again, just send me a quick note, and I'm happy to share it.
This is that Frankel article you're.
Yeah. Yep. Again, it just came out now. So, okay. So here's just looking at estimation of row and total proportions. Again, using Stata. So this is in a contingency table now. So if we go from just a simple frequency table to like if we want to look at a contingency table or a cross tabulation, we can also use the survey tab command to do that. Now, the way the survey tab command works for contingency tables, the first variable listed is the row variable. The second variable listed is the column variable. So in this contingency table, sex would be the row variable, MDE would be the column variable, and then I have options for what output I want to see. If I want overall percentages of the population falling into each cell, I can leave the options as they are for survey tab. But if I want row percentages, like for example, what percentage of males have had a major depressive episode, notice I need to add that row option to the survey tab command. Without that row option, I get completely different results, as you see in the table. So the first 4 rows of this table show the overall, the total proportions. So back to David's question, if I'm writing this up for paper, it would be incorrect to say that 40.6% of males in the population have never had a major depressive episode. That's not the correct interpretation of that parameter. I would need to say that 40.6% of the population is a male who has never had a major depressive episode. It's not conditional. I'm just describing one subgroup of the overall population and how prevalent it is. If I'm reporting row proportions, it's a different story. Now I can say we estimate that 15.1% of males have ever had a major depressive episode by adding that row option. Okay? But I get very different estimates depending on what option I want to request it. So just be careful with contingency tables when you're making these kinds of tables in SAS or in Stata. Okay. Questions about that code here for contingency tables? Any questions here? Okay, here's the corresponding SAS code. So notice in the table statement, I list sex first and then MDE second. And if I want row proportions, I just add that row option after the /. Otherwise, again, I'll get those weighted estimates of overall proportions. Okay, Now, here's a pretty critical example because what this example is illustrating is dealing with a chi-square test in the design-based approach, okay? So you've all probably at some point done a chi-square test where you look at the association between two variables and see whether or not that association is significant. So the point of this example is illustrating the design and adaptation of that chi-square test, okay? The way we would do this in Stata, again, declare the design variables. This can be done globally. I'm showing it in each example, but you only have to do it once in a given Stata session, okay? So declare your design variables, run your SVY tab command, row variable first, column variable second. So in this example, the research question is, do these education categories vary in terms of prevalence of alcohol dependence, specifically for this young subpopulation? So if I look at young adults between the ages of 18 and 28, is there an association between the amount of education they've achieved and whether or not they've been diagnosed with alcohol dependence? So that's the research question here. So we're looking at a contingency table where education is the row variable, alcohol dependence is the column variable, and I'm requesting row percentages. Now, when you use Survey Tab in Stata to do this kind of contingency table, you automatically get the most powerful chi-square test that's available, okay, adjusted for the complex sample. So in your output, you will automatically see that adjusted chi-square test. It's actually an F test. That's what's a little bit unusual to look at. You see that the design-based test is an F test with 2 degrees of freedom values. That's what you actually want to report for your test of association. It's no longer a simple chi-square test, okay? But that's how you can test the null hypothesis that those two variables are independent. Okay? In SAS, same basic approach. Remember that the domain variable has to be listed first, where you see age 29, okay? Then I have my row variable, then I have my column variable, and again, I'm asking for row percentages. In SAS, you actually have to add the chi-square option to get that design-adjusted chi-square test. In Stata, it comes automatically. Okay? So in SAS, we have to actually add that chi-square option to get the design-adjusted test. Okay, questions about that syntax for chi-square testing in this case? Questions about this? Yep.
Not about this directly, but if in cases where your dependent variable is continuous and you would run like an ANOVA or something across groups, like how does
there you would just use regression.
Okay.
You'd use survey regress with the categorical predictor. You'll get your F test out of it. Yeah. Other questions about the syntax? Okay, so this example is interesting because, like in the other examples we were looking at earlier, you arrive at some radically different conclusions. Okay, so first we see the descriptive table, the contingency table, where you see the weighted row percentages, the linearized standard errors, accounting for the design features. So it looks like on the surface that if you have less than high school education or you have more college or greater education, those are the groups that have the highest prevalence rates of alcohol dependence. The in-between groups, high school or some college, they're both at about 5%. Okay, looking at the standard. So it seems like there's this U-shaped relationship between education and alcohol dependence on the surface. Okay? If you were to report the unadjusted standard Pearson chi-square using the weighted percentages, that chi-square statistic would be 27.21. It's a big value. Okay, for this test of association, the p-value less than 0.0001. Okay? So the naive secondary analysis would say, wow, look at this association. I'm going to write a paper about this association between education and alcohol dependence, and I got all this strong support from the NCSR survey. Okay? Now, you redo that analysis, taking the design-based approach, and look at that design-adjusted test statistic. That F statistic is now 1.64. The p-value for that F statistic is 0.18. Again, you arrive at a completely different conclusion, depending on whether you take the design features into account or you ignore them entirely. Once we account for the design effects, the cluster sampling, the stratification, and the weighting, we no longer have evidence of a significant association between these two variables. Whereas it looked like it was a strong enough association to be robust to any comment you want to make about p-values if we ignore the design features. Now you might ask, why is there such a difference? That command will also give you some of these parameters that go into the design adjustment. The sample size here was about 1,275. There were 42 degrees of freedom, but here's the kicker. The average design effect, this generalized design effect, or GDEF, was 6.6. So on average, the variance of those estimated proportions was being inflated by about 6.6 times due to the complex sampling features. And that inflation and the uncertainty was not being accounted for in the standard Pearson chi-square test. That's the difference here. That's why we go from less than 1 in 10,000 to a p-value of 0.18. When we're fully accounting for that variance inflation, again, that came from saving money and the need to compute weighted estimates, we see a different result. So that's what's being taken into account here when you do this chi-square test. So if you get an F-test that's significant at the 0.0001 level, that means that association is robust to the sample design that was conducted, the use of weights and estimation, yada, yada, yada. And you have pretty strong evidence that that association exists in your population. Okay? That's not the case in this example. Okay? Everybody with me on that interpretation here? Jeff?
What is that A statistic at the bottom?
Right. So A, that is the coefficient of variation of the design effects. So briefly, the coefficient of variation is the standard deviation of those numbers divided by the mean of those numbers. So the standard deviation of those design effects is more than half of the mean. That's what that's saying. So not only was the average design effect big, but there's a ton of variability. So that means some proportions had a design effect of maybe 10. So the sample design was having a big impact on the precision of these estimates, and we need to account for that when qualifying the association between the two variables. Other questions about this chi-square test? Also very important to do this correctly with complex samples. Okay? Regression. So thinking about regression models, and I mentioned we'd come back to this. In SAS and Stata for linear regression, so when the dependent variable is continuous, like the case Jeff was just asking about, in SAS we would use proc survey reg. Okay? In Stata we would use SVY regress. And these procedures are specifically designed for continuous variables where you would roughly expect that they have normal residual distributions. Okay? So not for categorical, not for count, anything like that. These procedures are specifically designed for continuous dependent variables. Okay? Now, before we look at their examples, I want to come back to this Shakespearean question of to wait or not to wait. Okay? So some of you have already asked about this a little bit earlier in the short course. So as we've talked about, there's generally little debate in design-based approaches about the need to use weights for descriptive parameters, means, proportions, totals, especially if there was oversampling, where the weights are correlated with your key variables of interest. Okay, so that's not really up for debate. In the literature, there's much more debate about whether weights should be used when fitting regression models, the survey data, when your focus is on estimating relationships and associations between variables. This is where the economists and the design-based survey folks tend to butt heads. And that economists say, if you've done a good job and you've got your right theoretical model, who cares about the design features? And that's where there's more of an argument. Okay? So when your focus is on finite populations, and really this is the case in any kind of analysis, model specification becomes very important. So it's critically important to think about, have you done a good job of specifying the model, meaning functional form, nonlinear relationships, interactions between variables, categorical variables? Have you included all theoretically relevant predictors in a correct functional form in your model? When you're taking a design-based approach, remember the objective is to give you unbiased estimates of what the population would look like. Okay? So if you fit this model in the population and you do a poor job of specifying it, you'll get a nice, unbiased estimate of what that awful model would look like if you fit it to the whole population. Okay? So very simple, naive example. Suppose you had a curvilinear relationship between two variables and you fit a straight line to them. Okay? Then you use your weights. You're going to get a weighted estimate that's unbiased with respect to the sample design, just like we've been talking about all day. Okay? What that model would look like in the population if you fitted that bad model to everyone in the population. Okay? So unbiased with respect to design, but probably giving you a poor picture of what that relationship actually is. Okay? Now, if you fit that bad model without using the weights, you no longer have the protection. So now you have an estimate that's biased with respect to the sample design and doing a bad job of describing the population. You're wrong on both fronts. Okay? So at the very least, the use of weights in modeling gives you that protection against any biases introduced by the sample selection. Okay? So there's that. If you do a good job of specifying the model, like every single economist does, when you combine with weighted estimation, okay, that's going to inflate standard errors. Okay? So you harm yourself. You might fit the perfect model, you've done your homework, you've got the right theory, you've got the right functional form, and your weighted estimates look no different from your unweighted estimates. Okay? There's no information there, but the standard errors might double, triple, quadruple, whatever the case may be. Then you're artificially harming the precision of your estimates unnecessarily. This is the argument that others make.
How strong is the assumption that you've got a correctly specified model?
That's the $1 million question. Like I said, economists, it's always correct.
Yeah, I use the assumption.
Everybody else?
No,
You never know. You know, there's that famous quote that statisticians talk about that all models are wrong, but some are useful. In reality, you never really know outside of simulations. Okay? You've done your best job. That's where diagnostics is so important. You make sure you're doing a good job fitting the model. But what will happen if you do a good job, again, that simple nonlinear example, you actually fit the nonlinear model and you fit the data really well, the use of weights is not going to change your coefficient estimates. It's just going to inflate your standard errors. So weights introduce inefficiency. And the best example of this that I've seen is in this book on analysis of health surveys by Korn and Gabbard. In chapter 4, they use real data to show what can happen if you fit the right model, but you still use the weights and estimation kind of blindly. Okay? That's a really good example. I'm happy to share that with anybody. But that's a good example. So there's this issue of model specification, and the idea that weights give you protection against the sample design that was used in case of selection bias. So what do you do in practice given these kind of debates? In the 1970s, when there was a lot more of this kind of debate, it was very hard to fit these models using software. Okay? Right now, you can estimate them in milliseconds, literally. Okay? There's absolutely no excuse to check the sensitivity of your analysis to using and not using weights. Okay? It should be a built-in part of your practice. Is when you're fitting these regression models, do it one time with weights, do it another time without weights, and see what happens to your point estimates and to your standard errors. Okay? And I'm talking about how to look at that formally in a second. So if you see large changes in your parameter estimates, that suggests that you may have some model misspecification. It may not be the best model, and the weights are influencing what that relationship looks like. So in that situation, at the very least, you should be using your weights to obtain unbiased estimates with respect to the sample design. Small changes, on the other hand, in your estimates, combined with large changes in the standard errors, would suggest appropriate specification. You've done a good job specifying that model. The weights are no longer informative. You've accounted for whatever was in the weights that could have explained this relationship. And in that case, it'd be perfectly fine to report the unweighted models. Okay, the weights aren't offering you any new information about that relationship, but it's important to check the sensitivity of your results to these different approaches. So there's a formal test of the need for weights that you can do when fitting regression models. Here's how you do this. You fit an unweighted model, so ignoring all the weights. You can account for the other design features, stratification and cluster sampling. Fit an unweighted model that includes all your predictors of interest. These are your theoretical predictors, interactions, nonlinear terms, whatever it is. What you think the best possible model is. Fit that unweighted model. And to that model, add the weight itself as a predictor. You're literally adding that final weight variable as another predictor. And then you add all the two-way interactions between that weight and the other predictors that were in your model. So if you already have a two-way interaction between theoretical predictors, you add a three-way interaction between the weight and the two-way interaction. Okay? So you think about what's happening here. We're determining in this model if the weights moderate the coefficients fitted to your unweighted sample in terms of their relationship, the relationships being captured with the dependent variable. We're essentially testing interactions between the covariates and the weights to see if the coefficients change depending on the value of the weight. After you fit that enhanced model, if you will, perform a wald test only of the additional coefficients. So all those additional weight terms that you added, the main effect of the weight, and all those additional interactions, do a combined wald test of all of those coefficients. Okay? If that test is significant, that suggests that at least one of your coefficients is being moderated by the weights. It would be important to account for those weights in estimation. If that test is not significant, you can safely get by ignoring the weights in estimation. And you can see a theoretical result that relates that Wald test to a simple test of whether the difference in the weighted and unweighted coefficients is equal to 0. That was actually a homework problem in one of our classes. Okay? But it's very easy to do this using existing software because you don't need the design-based procedures. You can just fit the unweighted model, add these terms, and do a multi-parameter test of all those additional terms. Okay? And you can do this in linear regression, logistic regression. It doesn't matter. Okay? So that's useful in practice because that can give you a sense to go along with your kind of eyeballing of the changes in the estimates, whether or not it's statistically important to be accounting for those weights. Okay? Questions about that? That approach? Yep.
And this approach, would you still use SBY to?
Yeah, but just not the weights, right? So you can use SPY because then you're accounting for the impact of the design on these relationships as well in the standard errors. No. Yeah, you're just ignoring, it's unweighted, so you're ignoring the weights. Don't use the weights because then you're double weighting, if you will, if you use the weights for estimation. Other questions about this approach? So you might work with colleagues who put themselves in these camps about this issue. Don't do that. It's ridiculous because the camp idea dates back when it was hard to fit these models. Okay? Just examine the sensitivity of your results to these different approaches and make the best choice in terms of the efficiency of the estimates. That's the best approach. Okay, so that said, let's look at some examples of the linear regression approach. So this is getting back to N. Haynes. So the dependent variable is diastolic blood pressure, and the predictors are gender, race, age, and poverty. So just hypothetical. We want to see how these different variables relate to that continuous measurement of diastolic blood pressure. Here's how we set this up. Again, I declare the design variables in Stata. Only have to do that once, but I keep showing it here. Survey restricted to a subpop of interest, adults, age 18 and above. And then the command is regress, the linear regression. And in Stata, the dependent variable comes first. Okay? So the first variable listed is diastolic blood pressure. And then after that, you list all your predictors. And if you have any categorical predictors, they should have an I dot in front of them. That uses dummy variable coding or indicator coding for those categorical predictors. And by default, Stata leaves out the lowest value category as a reference category. You can modify that, and I'll show you how to do that. Okay? So we have race, marital status, gender, and age. Notice that I'm including a nonlinear term for age. I have age and age squared. I'm allowing for a nonlinear relationship of age with diastolic blood pressure. And then I can request design effects if I want. Okay, in SAS, I use proc survey reg. I declare my categorical predictors in the class statement. So there's an actual class statement within SAS. I declare my design variables, strata, cluster, weight, my domain statement for my subpopulation, then my regression model. The dependent variable on the left-hand side of an equal sign, followed by all the predictors. I can request the solution, design effects, and confidence limits for each of my regression coefficients. Okay? Furthermore, I'm showing in SAS how you can save the residuals if you want to do model diagnostics. So save the residuals, save the predicted values in an output data set called outdiag2. And it's still important in design-based approaches to carefully evaluate model residuals. I'll show how to do that in Stata as well here in a second. Okay, questions about the syntax, regress or survey reg? Yep.
Going back to slide 71, where the to weight or not to weight, where you have that kind of diagnostic test, the wall test on
Yep.
traditional predictors. So I just wanted to make sure I'm understanding. Should the wall test include the main effect of that weight?
Yes.
Okay.
Everything that you add to the model that you want to fit. So the main effect is weight and all the two-way interactions involving weight, but not the original predictors.
Yeah.
Just all the new variables involving the weight. That's it. Okay. Questions about the regression or linear regression syntax? Any questions about this syntax at this point? Hopefully you're all getting the common theme. Every procedure works the exact same way. I mean, not hard to do this. Okay. In Stata, if we want to do a multi-parameter test, after we fit the regression model, we can simply use the test command. This is a really handy feature in Stata. We just have to list the coefficients that we want to test against 0 simultaneously. So, it could be categorical coefficients, it could be continuous predictors, and that takes the design into account because Stata is calling on the weighted estimates and the linearized standard errors and covariances between the estimates. So this command automatically does that multi-parameter test. SAS does it by default for your categorical predictors, and you can also add a contrast statement to do multi-parameter tests involving other predictors. Okay, so this is a useful aspect of regression modeling because you can test blocks of predictors to see whether they even matter in the overall model. Okay, so this table just shows the overall weighted estimates, the linearized standard errors, their t-values, and notice that there are 15 degrees of freedom for each of the critical t-values, and Haynes offers 15 degrees of freedom based on the cluster sample design, the 95% confidence intervals, and then the design effects. Those design effects are pretty small for this regression model, and this is showing that debate. The sample design does not tend to have as much of an effect on regression coefficients as it does on descriptive estimates. But these are the weighted estimates. So we're exclusively looking at the weighted estimates in this particular case. You can see that several of these coefficients are very important when you fully account for the complex sample design. Interpretation wouldn't change. Everything you've learned about linear regression, logistic regression, same way of interpreting these parameters, you just talk about the population, not about the actual sample. Yep, Jeff?
Did I hear you correctly that the design effect was for N games, the same example was higher when you just had descriptive estimates?
A little bit higher. It was like 2 or something, 2.5. Yeah.
So like putting this in a multivariate setting actually
shrinks them somewhat.
Okay.
I mean, we have a lot of terms in this model. You could add even more. So it's just not as big of an influence on the variances that you see here. Okay? So in Stata, after you fit the regression model, you can analyze residuals. So these commands on this slide just show you how to save the residuals and the predicted values in new variables called e-hat1 and y-hat1. And then you can do things like look at a scatter plot, look at quantile plots, histograms, etc., just to check for outliers and things of that sort and make sure you're not misspecifying the structural form. You could do the same plots in SAS using that outdiag2 data set. I do want to mention that other regression diagnostics like Cook statistics, tests for collinearity, influence measures, this is an active area of research. So adapting complex samples to these measures that we all use frequently for diagnostics, that's still ongoing work. To my knowledge, the only software that's been written to do these advanced things, which come from recent dissertations in our program, is in R, where Rick Valiant, I mentioned Rick again, who's coming in November, he and his students have written a package for R called Survey Dynamics, SVY Dynamics. So using that package in R combined with the survey package, you can perform these design-based model diagnostics. And we show an example of how to do that in Chapter 7 of the second edition of Applied Survey Data Analysis. But unfortunately, that methodology hasn't yet made its way into any other software. So at the very least, look at residual plots, fitted value plots, just make sure you haven't misspecified the model outside of looking at these more advanced influence diagnostics and so forth. Okay, questions about this idea with linear regression? Any chat question? Okay, so that's linear regression in a nutshell. Logistic regression, arguably more popular for surveys. First of all, starting in SAS, we would use proc survey logistic within SAS, so not proc survey reg, but survey logistic. Again, you have a class statement. One thing to be aware of, though, if you're a SAS user fitting logistic regression models, the survey logistic command defaults to effect coding. It does not default to dummy variable coding when you use class variables. So you have to add the param equals ref option, and you can specify reference categories for your categorical predictors. Or you can just go with the default and interpret the effect coding. It's entirely up to you. Okay? But you want to be careful just with that kind of use of class variables. So I show an example of how to handle gender on that line right there. Then in the model statement, by default, survey logistic will model the probability of a 0. This is another key thing for SAS users to be aware of. I had a lot of clients who would come in a couple years ago and be like, why is every single coefficient in my model backwards compared to what I would expect? It's because by default, survey logistic models the probability of a 0. as opposed to a 1. So if you want to model the probability of a 1, you have to add that event equals 1 in parentheses to the dependent variable, in this case MDE. Otherwise, everything's going to be completely backwards from what you think you're actually modeling. Okay, and again, SAS automatically generates wald tests for your categorical variables as part of the output. Now, Stata gives you the SPY logit and SPY logistic commands. They do the exact same thing. I don't know why they do this, but they do. Okay? Logistic defaults to odds ratio output. If you like odds ratios, you can use logistic. Logit defaults to coefficient output. So if you like coefficients, use logit. There's an option in both of them that gives you the other one. So not really sure why they do that, but it is what it is. So you can add OR as an option to SPY logit, and you get odds ratios. You can add coef as an option to SPY logistic, and you get coefficients. You get the exact same results either way. Okay? And if you have categorical predictors, this applies to any of Stata's regression procedures. To set the reference category on the fly, just use IB and then the number of that reference category before the dot. And you're listing the different predictors. So if I wanted category 3 of race ethnicity to be the reference category, I would say IB3.race. And then we'll set 3 as the reference category using dummy variable coding. Okay. Another nice thing about Stata is that a graduate student of Lemeshow, some of you may have heard of the Hosmer-Lemeshow test of goodness of fit for logistic regression models. One of his graduate students, Kelly Archer, implemented a design-adjusted version of that Hosmer-Lemeshow goodness of fit test. Stata has since programmed that in the ESTAT-GOF post-estimation command. You can do a design-adjusted test of overall goodness of fit after fitting a model using SPY logit or SPY logistic. That's a nice global check of the quality of fit of one of these models. So it's nice that that's kind of built into Stata at this point. Question?
Probability or use the margins command, is there any time we need to be taking the design elements?
No, so the question was, when using SPY logit and SPY logistic, if you're interested in predicted probabilities or other quantities you can compute after the fact, the way that Stata operates, Stata saves all the most recent estimates and information needed to compute those predictions in memory. So as long as you've used the weights and the appropriate design features in generating the estimates and standard errors, those will be saved. So when you use margins and margins plot and so forth, those commands are referring to the most recent fitted model, accounting for the weights. So you don't have to do anything special with margins and margins plot, just use them as is to look at graphs. Yep.
Is that also true for the standard errors of the prediction that margins?
Yep, because they're calling on the variances that were part of the actual model fitting. Right. That's a nice feature too. And we illustrate that in the book here as well. Okay, so here's just our final example, and then we have a couple minutes for some questions as well. So our dependent variable here in the National Comorbidity Survey data set is MDE again, that major depressive episode indicator for yes and no. And then we have a list of sociodemographic predictors, age, sex, whether they've ever been diagnosed with alcohol dependence, education, and marital status. So Stata again, I could use SPY logistic or SPY logit, depends on your personal preference. Notice that the first variable after the command is the binary indicator. Stata will not accept anything but a 1-0 variable. So if your dependent variable is 1-5, it's going to complain. So it has to be coded as 1-0. You list that first, then your list of predictors, and notice how I'm using IB2 for sex to set 2 as the reference category for sex. Okay, so I can use either way there. And survey logistic and SAS will give you odds ratios and coefficients by default. Okay, so in survey logistic, I again declare my design variables. I have my class statement with explicit reference categories and reference parameterization for dummy variables. Then I explicitly model the probability of a 1 in my model statement, and everything else is as normal. Okay, so just some slight tweaks to the overall survey logistic command to fit the exact same model. Okay. This slide just shows the weighted estimates of the coefficients, the design adjusted standard errors, so I can see what's important and what's not. This slide just shows the odds ratios. So these are the weighted estimates of the odds ratios in that logit model and the corresponding design adjusted confidence intervals, fully design based, fully accounting for the complex sampling. Okay. I can make inference about which of these odds ratios are in fact different from 1. And then here are those after the fact wald tests for the different categorical predictors. And it looks like when you account for the design that education does not matter in this particular model. So I'd failed to reject the null that any of the education coefficients matter in this particular model. I can keep age and marital status if I wanted to trim this logistic model a little bit. Okay, here are the references that I've been referring to over the course of the morning here. Again, that model-based versus design-based article, applied survey data analysis, some of the analytic error work that we talked about, the survey weights book that I have up here on the table, and yeah, the remaining 3 are on analytic error. So if anybody would like electronic copies of these or the other new papers that I mentioned, I think we're going to post some of the new papers on the PDHP website, but if you'd like to see copies of any of the other articles or take a look at these books a little bit further, feel free to just shoot me an email. Let me know, and you can. I'd be happy to share these with you. Okay, so that's it. Any questions or comments now that we've hit 1 o'clock here? I know there's a lot to go over, but hopefully everybody kind of found some common themes today. It's pretty straightforward to account for these design features and analysis, so we're going to try to keep that moving here. Yeah. Yep. Yeah.
So that if you have a combo binary outcome, then the modified Poisson regression will be preferred. So what do you think about this?
What kind of binary outcome did you say?
Modified.
Modified?
Modified Poisson.
Yeah, I'm not familiar with that, so I'm not sure. Yeah. So regarding specialized procedures, if you need specialized routines to fit these kinds of models, the question that you should always be asking is, has that routine been modified to incorporate weights and estimation? Has it been modified to account for these design features? Because a lot of more specialized commands, they may be written for simple random samples, but they may not be adapted to this procedure. So if that kind of modified logistic regression, there may be commands for that, but just ask that question, if it can account for these features. Okay, I want to mention too, the evaluation forms that Paul mentioned at the beginning. We can hand those around, or the people online. Like, we're going to send you evaluation forms just so you can give us some feedback about the workshops and maybe suggestions for future workshops as well. So. Okay, so thank you everybody for listening. If there are no further questions, I think we're all set then. Thank you.